Today we're going to look at applications of differentiation, and it turns out it has some very far-reaching consequences. Um, so let's imagine we've got a farmer and they want to build a rectangular pen for some animals, and they've got 100 meters of fencing. Now there's going to be and also one side is going to be against a wall. Find the dimensions of the pen enclosing the maximum area. Well, there's some really bad ways of doing this. They could, I don't know, make the pen really, really, really long, but kind of not coming out very much. Or they could make the pen come out loads, but then not be very wide. There's probably going to be a happy medium where they're kind of coming out somewhat and coming back in. And the question is, how can we find that? And actually, we can use differentiation to find that. So, if you have got any farming buddies or you're a farmer, then you might talk to them about this, how they can possibly maximize the rectangular pen, but it can be used in so many other ways as well. How can we do this then? So what we want to do is maximize the area. And we've been talking about maximums and minimums in recent lessons. Those are our stationary points. So I need to try and write down a function that I can maximize. Now at the moment, all I've done is I've got my pen and I've labeled this bit X, okay? Which means that this is going to be X as well because it's a rectangle. But what is this going to be? Well, for the moment, I'm going to call it Y. However, I know that I've got 100 meters of fencing. So I've got X, Y at the moment, but I want to get rid of this Y because I just want a function of one variable. I know I've got 100 meters of fencing, so it must be that 2x plus y is equal to 100. And that means y must actually be 100 minus 2x. And in some ways, it's best to just get rid of it now, get rid of that y, and label it in terms of x. Whoops, 100 minus 2x. And so the area is going to be x times 100 minus 2x. And suddenly this is turning back into being something we know how to deal with. We have a function of x and we can try to maximize it. And to do that, we need to find out what dA by dx is. Let's just recap. Actually, let's just think about this, because at the moment I've got a. Instead of y, I've got a, but it is a function of x. Now I know that it has a root at x equals 0, and it also has a root at 50, because when I set this thing equal to 0, I'll get 50. I also know it's a negative quadratic. So this is what it's going to look like. These are all physical possible values of a. I can't actually have x as being negative, so even though it would carry down, it's not a meaningful thing in this situation, nor is it meaningful to have a length x greater than 50, because then I'd get negative one of the other ones, because I'd get 51, 51. Well, that's already more than 100 meters. Okay, so you might already be thinking, actually, how can you work out the maximum? We know about the symmetry of the quadratic, but I'm going to leave that for the time being because I want to focus on differentiating. Okay, to differentiate this, I'm going to need to first multiply it out, and it's going to be 100x minus 2x squared. So that means dA by dx is 100 minus 4x, and that equals 0 for my stationary points. In fact, there's only going to be one stationary point here, but let's just write stationary points. And I can solve that, and x is equal to 25, which, by the way, makes sense because that is the line of symmetry that goes through the quadratic. X equals 25. Okay, and that means that I know I can now relabel these. So this is 25. This is going to be 25 as well, and this is going to be 50. So it actually makes sense when you have a wall to make it 50 meters along and 25. Why not a square? Because that seems a good shout as well. And then I get 33.3 recurring as both of my sides. But in this case, okay, this one works best because I get the wall for free. So it makes sense to use not as much of the wall as possible, but like more wall than you would if you had a square. So if I work out the area, although it doesn't actually ask me for it, the area of this is 1,250 meters squared using my 25 and 50. Whereas if I do the other one, then I get 1,111.1 recurring meters squared. So actually I lose quite a lot of area. And that is an application of differentiation. We can use it to maximize the area to solve a physical problem that could be useful. And it turns out that there's things that go well beyond this. If we can find the maximum, then we can do a bit of, we can actually do something really useful and just make life easier for ourselves, basically. Such as, how about maximizing the shape of a car designing the shape of a car to minimize, instead of maximizing, to minimize air resistance. Then you can make a faster car, for example. So that's what people are doing on a day-to-day basis. It gets quite a complicated problem, but that will allow you to have a faster car, allow you to sell, better products, essentially. I'm not going to go into this anymore, but you might want to look into this as a little challenge. Can you prove that a square, when you don't have a wall, can you prove that a square is the best rectangle to maximize the area? So if I said I've got 100 meters of fencing but no wall, can you prove mathematically that this should now be 25 by 25? Let's look at slightly more complicated examples. So moving away from area and moving on to 3D shapes with a cuboid. So please pause the video, have a go at this question first, see if you can do any of the parts. If you get stuck, then watch for a little bit and see if you can get some hints, but try and do as much as you can. Okay, first things first, I'm going to just sketch a cuboid out. Now I know that it's got an open top. Okay, so I've just got I've got 5 faces to worry about. The height of the tank is X, and I'm also told that 2 opposite vertical faces are squares. So let's go with the left-hand side and the right-hand side. So that's also going to be X. But I don't know what the other length is, so I'm just going to call that something else. I'm going to call it L for the minute. However, I do know that the surface area is 54 meters squared. So if I can write down an equation for the surface area, then I can get L in terms of X, because at the end of the day, I want the volume, and that is going to be X squared L. So let me just recap. I've got the volume in terms of X nearly, but no, I've got this L here. So I need to get L in terms of X, and then I can substitute that in. So let's do this. The surface area, that's going to equal my 2 sides. So I've got 2x squared. And then I've got the bottom is Lx, and these 2 sides are Lx. So it's actually 3Lx. Remember, there is no top. And that is equal to 54. Brilliant. I've got an equation I just need to rearrange and make L the subject. So 3Lx is going to be 54 minus 2x squared, and L is going to be 54 over 3x minus 2x squared over 3x. Note, I've just chosen to divide each term straight away by 3x instead of writing it as a single fraction, because then I can split it up. This is absolutely fine. That leaves me 18 over x, if I cancel that down, minus 2/3 x, or let's write it as 2x over 3 for the moment. Okay, that is my L. So therefore, I'm nearly there. The volume is going to be x squared times 18 over x minus 2x over 3. and that's going to equal 18x minus 2/3 x cubed, which is exactly what's needed here. Okay, brilliant. So I've got the answers. Quite a lot to do there, but I've managed to get the volume just in terms of x. Okay, now even if you couldn't do that, you're like, oh, I don't know how to do this, or you make a mistake, we can still do parts B and C. So if this does happen in the future and you get stuck, you can still get some credit. So we've done part A because now we can quote. It's a show that question. So we had to see where it comes from, show where it comes from, but now we can just use that formula that we have. Okay, so now we're trying to find the maximum or minimum value of V. Okay, for that we're going to need to differentiate. Yeah, dv by dx is 18 minus 2x squared. Okay, I'm doing this quite quickly. I've times 3 by 3, cancel that with that divided by 3. And that's going to equal 0. And actually, I'm going to write for max or min here, because they've sort of told me that. I could write stationary points if I want. So I think I'll solve this by getting x squared by itself. I'll show you another way in a second that I could do it. So 2x squared equals 18. X squared equals 9. X equals 3. And I'm straight away going to reject minus 3. Because x is a physical thing here. It's a length. Another way you could have done that is you could have divided through by 2. I'm just going to do it up here. You could have divided through by 2, done 9 minus x squared equals 0, and written it as a difference of 2 squares. Sorry, it is a difference of 2 squares. Factorized it accordingly. And then got that x is equal to 3 from that, just a reminder. Okay, brilliant. We've got a value of x. But now we need to know the max or minimum value of v. So I can substitute that back in. Max min value of v will equal 18 times 3 minus 2/3 times 3 cubed, which is 54 minus 18, because I can cancel one of those out, so it's 2 times 9, 18, and that's going to give me 36. So there we go. It's in meters cubed. That is the max or min possible value. And in fact, it's going to be the maximum value, because I could actually make the I could make it as small as I want. I could make it 0 by like making the height really, really small, and I could still get a surface area of 54. We're not interested in the minus 3 one. So part C, justify that it is a maximum. Okay, and I jump straight to d2v by dx squared. That's going to equal minus 4x equals minus 144 when x, hold on, what am I doing? Not minus 144, I've substituted the volume here. Okay, but it's definitely going to be negative. It's going to be minus 12 when x equals 3. So maximum. And there we go. We are still doing the same kinds of things we've been doing in recent lessons, differentiating, finding the second derivative. So really the new thing about today is creating this equation that we then differentiate. That's, to be honest, that's probably the hardest bit at this point, because there could be lots of things going on. It might not be just a cuboid, but this is what you're going to practice in this lesson. And again, so we can, given a sheet of metal of 54 meters squared, we found out the maximum possible volume if you have a square sides here. These things can be quite useful. So we have the dimensions that we should use. I suppose let's just talk about them. It would be 3 by 3, and then L would be what would it be? 18 divided by 3, it would be 6 minus 2, I think it would be 4. Okay, and that would be the best way of maximizing the volume for this cuboid. Brilliant. So another application of differentiation. I hope you're happy with it. Try some questions.